All right, we'll go ahead and get started. I just want to thank everyone for joining today. This is we're calling it quarter 3 HMS webinar, although I guess technically we're a couple weeks now into quarter 4. We are going to be focusing this discussion on hypothetical storm modeling, and there will be 4 of us presenting. I'm Josh Willis, and then we'll have Tom Brower, Lauren Coe, and David Ho present parts of the presentation as well. Before I get started, just a couple of announcements. This webinar is being recorded. Probably within the next week or so, we will post the recording on our website, so you can refer back to it if need be. We have everyone muted just to try to minimize disruptions, but we highly encourage you to take advantage of the chat feature throughout the presentation. We have several members of our team on, and we will do our best to answer in the chat. And then at the end of the presentation, we have some time set aside for more Q&A. So with that, let's go ahead and look at the outline for today. I'm going to kick things off with a quick introduction of hypothetical storms. Then I'll hand it over to Lauren to talk about the hypothetical storms R&D work unit. The majority of this webinar will be showing off features in HMS that are related to hypothetical storms that came out of the work unit. And there's roughly half a dozen or so that we'll be highlighting, and we're trying to present them roughly in the order that you might use them in a typical study involving hypothetical storm modeling. And then, as I mentioned at the end, we'll save time for some questions and discussion. All right, so let's get into an intro. Starting off, pretty basic, what is a hypothetical storm? And it is simply a storm that hasn't happened yet. And use them all the time as hydrologists and engineers. We use them for design, for risk and flood analyses, and also for emergency preparedness. Hypothetical storm modeling is difficult, and it requires a lot of assumptions. So I always like to kind of start off these discussions with an analogy. So I'd like for all of us to use our imaginations for a second. We're not in an office or in a bedroom at home. We're currently walking through a small section of a very large forest. And then after our walk, we are asked 2 questions. We're asked to estimate the height of the tallest tree in the entire forest. And then also we're asked to estimate the height that only the tallest 1% of trees exceed. And so these are very tough questions, right? Did we see the height of the tallest tree in the forest on our walk? Probably not. Did we see trees that would be considered in the 99th percentile in terms of height? Maybe, maybe not. We have to make a lot of assumptions and kind of extrapolate well out into parts of the forest that we haven't seen yet. And so this is very similar to what we do for hypothetical storm modeling, giving a very short period of record for observed storm events. Usually we're lucky if we have 40 to 50 years of good storm data. We're commonly asked to estimate the largest theoretical storm event that could occur at a specific watershed. If you've ever done probable maximum precipitation studies before, this is what you're doing. And then also there are times where we're asked to create a storm and then tie a probability to it. To be used for designing different infrastructure, assessing different risks. And so we have to make a lot of assumptions about what depth we use, what duration of storm do we use, what kind of patterns do we give our hypothetical storms. So a lot of assumptions. These types of analyses, the more data, the more observed data from actual storm events that we can use, the better that our hypothetical storms become. And luckily here recently, we've introduced a lot of new tooling into HMS, thanks to the hypothetical storms R&D work unit. And so that's what we're going to focus on for the rest of this webinar. And with that, I'm going to kick it over to our project manager on the HEC side for Hypothetical Storms work unit, Lauren Coe. She's done a great job of PMing, and she's also been responsible for several of the features that we'll be demoing today as well. So with that, off to you, Lauren.
Cool. Thanks, Josh. Yeah, so I'm Lauren Coe, and I'm just going to give a brief overview of the work unit. So our work unit, the official name is the Improved Hydrologic Modeling of Probabilistic Storms. It is funded through the USACE Flood and Coastal Systems R&D program. And so as Josh already kind of alluded to, the main aim of our work is to provide more practical and technical guidance and recommendations for hypothetical storm modeling. A big part of that is being able to incorporate more modern precipitation and analysis techniques, because as a lot of us know, some of the guidance can be a bit outdated and a little bit out of date with, the kind of data we have available now. Specifically, we really want to be able to develop tools that are watershed specific for the application of hypothetical storms. And another core component of our work, or an objective, I should say, was being able to capture uncertainty, not only in the storm parameters, as in, like spatial and temporal patterns, but also in the model parameters that are kind of driving the hydrologic processes. So uncertainty incorporation into hypothetical storms is a big part of this work unit as well. And then finally, we wanted to be able to incorporate into our workflows the kind of data that users like you modelers are already used to. So we want to be able to integrate these widely used sources like NOAA Atlas 14 into our workflows as well. So this is for FY26, this is actually the third and final year for this work unit. And the kind of the tasks that we have as part of this and all the deliverables kind of break down into these 4 tasks. I won't read them all, but when we look at the deliverables that are coming out of this, we're going to really highlight some of the cool software features, but just know that a lot of it is technical reports, tech transfer guides, design documents for future future like software development, because we really want to like fully encompass all that's needed for users to be able to more accurately model hypothetical storms. So I will just talk about a lot of the features that have come out of this. So we're looking at 10 plus features listed here. There's more that I wasn't able to list, but just to briefly overview. So we have frequency storm modernization enhancements. We've had a new sampling technique and uncertainty analysis with copulas. We have a variety of new sampling and uncertainty analysis. So you're now able to sample hypothetical storm spatial patterns, temporal patterns, area reduction functions. All of those new techniques came out of this work unit. And then additionally, coming out of this final year, we have a new area reduction method, the parametric area reduction method. That allows you to define and parameterize a site-specific relationship that's a function of storm area and duration. So if you look at something like TP40, where you're kind of limited in the storm area and it might only be defined for a single duration, this is going to be a lot more generalized and site-specific for your specific project. And then finally, going along with that, you're able to sample those area reduction parameters from that parametric equation as well. And then finally, we have the features that we're going to look at today. So I won't go too much into those, but these are all, these like 5 or 6 final features are all coming out of this final year of the work unit. So with that, I'll let Tom kick us off and get into the demos.
All right, thanks, Lauren. I'm gonna let Teams update. Hopefully you can see my screen soon. Or can you see it now? Okay, great. All right, so whenever you're doing hypothetical storm modeling, one of the first steps is to calibrate your model to several events that are of similar magnitude to that hypothetical storm that you're trying to model. So the next features I'm going to show are pretty basic, but they're really aimed at making calibration easier and faster. And with that, we've added a USGS Streamflow import option. So to access that, this is in version 4.14, beta 1 and on. But to access that, it's going to be the tools data menu, and then I'm going to go to gauge USGS import. So I'm working here in the Truckee River, and with this dialog, what I can do is set up a query that will query the USGS server for gauge data. I'll show you the first option. I can query, I need to just set a spatial bounds for my query, so I can do that with an existing basin model. I'm going to use this one that's in my project. I could optionally use a shapefile. And then there's also a buffer arg there. So if I wanted to buffer that, I can. Now I need to also bound the search in time. And to do that, I'm just going to use one of my control specifications that are already in the project to set the time bounds for the query. I have options for continuous data or daily data. So continuous is anything that's less than daily, according to USGS. I should also mention that I have options to select between flow and stage. So here I'm going to use flow. There's optional argument for a API key. So if you're doing these routinely or frequently, I highly recommend you get the API key from USGS. They just give you a better rate so that you can query the site more frequently without getting penalized. And so I did my query, and these are the sites that are returned. So I can see, I think it's 50 some odd sites, and start time and end time for all those. If I were doing a longer duration, maybe some of the gauges wouldn't quite be there for that entire window, like this one here. But there's the sites that the query found. And then I have an import options dialog. And so here, these are just, if you squint your eyes, you can kind of see some DSS looking fields here. So we have A through F parts. I can customize A, B, F part. C is set based on the parameter itself. These are all those sites. I can optionally set a different time zone. So I can do universal coordinated time or GMT, and then I can also set one of local time zones, standard or daylight. We highly recommend doing everything in GMT. It solves a lot of problems. So I'm just going to keep it that way. I can also rename the gauge here if I would like. And then here I'm able to specify a DSS file for where this data is going to be imported to. So I went ahead and ran the import. And right now this is reaching out to the USGS server and pulling the data in. All right, so the import completed. I see some notes about the gauges that were created, and then a few notes that said, hey, we went out and queried the site, but we didn't actually find any data, so we didn't create a gauge. I'm just going to close that. I can close my query dialog, and then in HEC-HMS, I'll browse to my time series data, and now I should have some new discharge gauges, and these map to those names that we specified in the import options dialog. So I can take a look at any of these, and just like always, I could go just take a look at that data. So if I want to see a graph, I hit the graph tab here, and I can see a graph of the outflow. So that's a nice feature for importing the data. And then the next thing we added as part of this work unit is a dialog that allows you to map these in a global way. So this has never been a part of HMS before, but now you're going to see I selected the basin model, went to the parameters menu, and now I'm going to click on observe data, and I get what's called the observe data dialog. And so here for each basin element, I can specify observe flow, stage, or SWE gauges. So a typical workflow would probably be something like select all of the junctions in the project, and then I have a drop down where I can select the gauge. Now, the nice thing about what's been done here is these gauges are sorted by proximity. So the first gauge in the list is probably going to be the one that's closest to the outlet of South Lake Tahoe Basin element, or that junction. Likewise here, we'll see, yep, Trout Creek is the first one in that list. Nice. I'll go on down to something like Reno, the first one in that list, Truckee River at Reno. So it's a way to just quickly map, observe flow to locations and doing it in a global basis. All right, that is my demo. So I'm going to pass it on to, I think, David.
Awesome, thanks, Tom. All right, so hi everyone, my name is David Ho, and I'm excited to talk to you guys about the storm pattern extractor. So this tool helps with supporting creating custom storm patterns for the hypothetical storm meteorologic method. So HMS provides you an option to set your own user-specified temporal pattern using percentage curves when you're using the hypothetical storm meteorological method. And if you ever tried creating a custom pattern before, it can be cumbersome finding a pattern from a time series gauge, then normalizing the pattern as a percentage curve so that HMS can read it. So we now automate the process. So as long as you provide HMS a precipitation time series gauge, you can create this percentage curve. So some use cases for creating custom patterns. If you want to use a historical pattern for creating design storms. Historical patterns, some of the benefits of using historical patterns are it can create more realistic looking floods, especially when you're looking at longer duration storms. Another use case for this is if you want to set up a sensitivity analysis to analyze how storm patterns affect the peak outflow. We often talk about how storm patterns are highly sensitive to your outflow results, so doing a sensitivity analysis can help you see the range of possible values. So the storm pattern extractor has two filtering options. We have a depth and duration option and depth and annual maximum option. So the depth and duration option, this lets you select storm patterns based off a given duration and depth threshold. So an example would be you want to find all storm patterns that are 72 hours in duration, and the 72-hour depth is equal to or greater than 8 inches. The depth and annual maximum option finds the annual maximum pattern for a given duration. So an example would be find me the pattern that creates the annual maximum 72-hour depth for water year 2020. You have the ability to edit the storm patterns and view its timing relative to other storms. And then it saves your pattern as a percentage curve, which can then be used in hypothetical storms. This version, this feature will be available in 4.15. So it won't be in 4.14, but we'll have this a beta version of 4.15 soon after the 4.14 has been released. Okay, with that, I'm going to move to doing a quick demo on the storm pattern extractor. So here I have a watershed that is the San Lorenzo watershed located in Santa Cruz, California. It is currently nighttime here. I have the meteorologic model set to hypothetical storms, and I'm going to try and model the 100-year depth, well, 100-year storm. So here with the hypothetical storm method, we have all these different parameters we just set, and we need to specify a temporal pattern. One thing to note is we are looking at a storm duration of 48 hours. So we determined that 48 hours was a critical duration for this area, but I need a pattern for it. So with this tool, the first thing I will need to make sure I have is a precipitation gauge. So I had created a basin average time series gauge for the San Lorenzo watershed using the AORC dataset. So I took those grids from 1979 all the way to 2024 and did a basin average created basin average time series using the Vortex grid to point tool. So to access the storm extractor tool, we also go to tools. We'll have this precipitation option and then storm pattern extractor. And so you have the wizard window open for the storm pattern. If you've ever used the snowpack tool, this wizard follows the same pattern or the same conventions as the snowpack. So you can thank Melissa Micah, who had designed the snowpack tool. Right, so the first thing that you'd set is your unit system and setting your precipitation time series gauge. So here I have my precipitation AORC basin average time series. I'm going to click next. So here you can set the analysis time window. At default, it's going to give you the entire period of record, but you can just say I want to analyze a shorter period of record. Click the update button and it will update for you and you can move forward with that. I'm going to just stick with the entire period of record, so I will just not have anything there. This step is where you can extract the patterns. Right? So we have the two options, depth and duration and annual max and duration. I'm going to choose the annual max and duration first. So the only setting you need is the duration. So how long do you want this pattern to be? So in this case, I want it to be 48 hours. I'm going to click filter. And what this does is it's going to look at the max 48-hour depth. It's going to go through my time series, look at the max 48-hour depth for every water year, and then choose the pattern that created that max 48-hour depth. So here I can just look to see what that pattern looks like. So here for the 1982, this is what the max 48-hour depth pattern looks like here. All right, I'm going to move over to the depth and duration. So with the depth and duration, you need to specify two parameters. Again, it's the duration, how long you want your pattern to be. And then the second thing is the depth threshold. So the depth threshold, this is looking for any pattern that equals or exceeds your specified depth threshold. So what I'm going to do here is I'm going to go to Atlas 14, and I'm going to look for Santa Cruz, the San Lorenzo watershed location, which I have specified already. I'm going to look over at the 100-year, because I'm interested in the 100-year and 2-day duration. And that gives me, it says a depth of 9.55. So with my threshold, I'm going to specify 9.55. Filter, and it finds one pattern, right? So the 1982 pattern. So this also happens to be the largest flood of record as well within this watershed. So it makes sense that this would also be the largest storm. Right? And this is the pattern that generated from there. Now, I might be still interested in looking at more patterns than just this one here. So I'm going to come back and look at my table, and with rainfall frequency, there's always uncertainty in the depth itself. So I'm going to look at the uncertainty range where it says 8.12 and 11.5. So I'm going to use the lower threshold of 8.12 and see what patterns come up from there. Click filter, and I see that now there's 6 patterns that come about. Right. So I'm going to choose these 6 patterns and move forward with the next step. So here, the next step, we need to now process the data. So we have these 6 patterns that we can look through. And so this follows the snowpack convention, where we require you to look at the data prior to moving forward with it. The status has 2 selections. You have either raw or processed. To process the data, you simply just have to click the compute button, and we now have our data processed, and you can move forward with it. You also have the option to make edits to the percentage curves. So here on the bottom, we have this table of your percent time and your percent depth. So I can change the values for the percent depth, click compute, and process that data. And so it will move forward with the data that I had just edited. We can also look at the table 2 table here to see what edits were made. In this case, I want to use the raw data set. So I'm going to clear my edits, say yes, and just click compute and just use what originally was there. You can also toggle between percentage or accumulated. What this does is you can just look at what the actual accumulated depths are. So in this case, this storm depth 86 gave you a depth of 8.99. Our 82, which was our largest storm, was 11.11, and so on and so on. I'm going to just move forward with the original depth for all of the patterns. So I'm going to click compute all to process all the storms and move on. This step here just lets you look at all of your patterns in one table. And so what's nice about this is you can click between percentage curve and incremental pattern, and then look through each of the patterns to see how the distribution, what it looks like. So here we have like a center-loaded storm. For the 86, it's more of a front-loaded storm with a little bit happening in late 50% of the later on. Here we have a dual pattern storm, and so on, where you can look at all of them. So I'm going to select all of them and move forward to the next step. And here's where we can save the data. Here's where you can save to a specified DSS file. And then the paired data name is where you can assign a name. The default name that we give has the date of the storm. So we have the 82 that happened from January 3rd to January 5th. I'm going to use the default names and click finish. When that happens, we can look over to our paired data, percentage curves, and we have the curves then imported here as percentage curves. So we have all 6 here. We also append the duration of the storm. So I had set a 48-hour duration, so 48 gets appended to my storm. All right, so with that, I can then come to my hypothetical storm and then choose of the 6 which pattern I want to use. For this purposes, I'm going to choose the 82, which happened to be the largest storm in this area. Head over to my simulation. I have a 100-year simulation already set up, and click run. Right. And then over to my results, I can then look at the outflow from my 100-year storm event. Okay, with that, I'm going to end my demo here. But I also want to note that you can, with these patterns, do an uncertainty analysis, set up an uncertainty analysis, and sample from different storm patterns. So in this case, we had 6 storm patterns, but with the extractor, you can select from a lot of other patterns given your threshold criteria, and then do a uncertainty analysis to see how your storm patterns can affect your peak flow. Another thing that you can do is you can create these percentage patterns. So again, creating extracting a lot of storms from your data set, and then finding percentage values out of your historical storms. This is the way that Atlas 14 creates its patterns. And so you can also create your own custom patterns as well using this tool. All right, with that, I'm going to pass it over to, I think it's Lauren, or is it Lauren or Josh?
I think it's Josh.
All right. All right, thank you, David. Grab the screen. All right, so this is a good segue into our next feature. So similar to the tool that David just showed off that extracts temporal patterns from observed events, with this tool, we can now extract depth area reduction curves from historical storms. So this is now automated in HMS. Before, my workflow was I would typically go into MetView, which has good tooling for computing depth area duration tables and DAR curves. But just that process of kind of leaving HMS, going to another software, and then coming back to HMS was very time consuming, probably 30 minutes or so. And now with just a few clicks, you can have very similar functionality in HMS. So with hypothetical storm modeling, David showed off, some commonplace that we go to for our depths is NOAA Atlas 14. But when we apply those point rainfall depths to wide water or large watersheds like we're typically dealing with in USA studies, it's very important that we have these curves to reduce point rainfall to area rainfall. And so this is just an example of what we get after we run the extractor tool. Go to the next slide. All right, so one of the ways that you can access this tool is just a right-click option in HMS. So if you have a gridded precipitation MET model set up with AORC data in this example from July of 2024, you can right-click. If you didn't know, we have an accumulated precipitation option that I think Tom developed several years ago. You can compute a raster that has accumulated rainfall depths values. But now with this new feature that'll be available in 4.15, we also have the option to compute a depth area reduction curve. So that will launch a two-step wizard. In the first step, you choose your critical duration. The tool that David showed for the temporal pattern extractor handles long continuous simulation data very well. This tool here is more designed for single events. You could use it on a gridded data set that spans many, many years. It'll just take some time, so you'll have to be patient. So what this does when you set the duration is it will move a sliding time window through the whole gridded precipitation data set, and in this case, find the most intense 24-hour period to use for its accumulations. We have two different methodologies currently for accumulating precipitation and computing depth area duration tables. The first is center out accumulation. This is similar to what MetView does. It kind of disaggregates storms spatially and moves cells with intense rainfall closer together in its calculation. So it will always be the more conservative or less steep depth area reduction curve. Center out accumulation works well for radial, well-defined events, kind of like tropical storms that tend to be circular with a very clear bullseye. So that's when I would use center out accumulation. Convex hull is a good option if you have a storm that has multiple intense centers or is kind of random and sort of messy, so to speak, elongated and doesn't really follow a defined pattern. Optionally, you can choose to bound the area that you're computing the depth area duration table if you provide a shapefile. And then on the second step, you simply give it a name. And then it will compute the depth area duration table and curve for you. So this is an example of the output. I did this for 5 different historical events, and that all happened within the same small watershed that I was testing this feature with, and you can just kind of see the difference between those 5 events and depth area reduction. So this is definitely input into a hypothetical storm that can have a large effect on the output. All right, I will pass it over to Lauren.
Okay, thanks again, Josh. So I'm going to talk a little bit about the cross-validation compute feature. So just a little bit of background on it and kind of maybe some definitions of what a cross-validation is. So if you think about the traditional validation approach, it might be something where you have a total of 6 events. You will calibrate to 4 of those events, do some kind of averaging of those parameters, and then you'll validate to the 5th and 6th event. In a cross-validation, it's a little different because you're going to basically validate any given calibrated parameter set against all the other events that you have. And so you, instead of something like this, you get all this cross-validation where event 1 parameters are applied to event 2 and 3, 2 parameters are applied to event 1 and 3, and so on. What that kind of lets you do is it's going to highlight the parameter sets that do well or don't do well in representing Bayesian response for other validation periods. And that becomes very important, right? When you're doing hypothetical storm modeling, because you want to have the most representative parameter set for your hypothetical storms. Okay, so why the cross-validation compute? So when we do validation, it's typically done by creating these Bayesian models and copying the global editors. The pain point in this are the initial conditions, because in order to apply, let's say in this example, we have a December 2015 event. If we want to apply the December 2015 event to the January 2009 Bayesian conditions, well, we have to preserve the January 2009 initial conditions, right? Things like initial deficit, reservoir elevations, and things like that. So what you end up having to do in the old workflow was create multiple Bayesian models to handle this. So if you wanted to cross-validate 6 events, you might end up with 30 different Bayesian models, additional Bayesian models for something like that. So what the cross-validation compute does is it automates this swapping of calibrated parameter sets while maintaining the initial conditions to compare the performance under different conditions. So there's not extra work really beyond calibrating to your events in your typical simulation run and then creating a cross-validation analysis. It's all kind of done under the table. Okay, a little more background before we get to the demo, just so we're on the same page with the naming convention when we start to look at the demonstration and the results. So the naming convention is based on the Bayesian model names. So your first Bayesian model is going to be your initial condition member Bayesian model, right? And so that is going to define your MET model, your control specs, initial conditions, and any observed gauge data, right? Because we want to see the 1994 conditions. But the second one is your validation member Bayesian model. And so that's all other element parameters. Think things like your transform parameters, like your time of concentration, your storage coefficient, your constant loss rate. That's what we want to validate. So just when we look at it, just understand that's kind of the naming convention there. And then before I hop in, I'm going to hop into the demo, but just for your reference, there's a little bit of like a glossary here because as I refer to different things, the names can get a little confusing. But just so you kind of understand what I'm talking about as I'm explaining things during the demo, and then also on the next slide, if you want to take a look at, these are the initial conditions that are predefined in HMS. So these are the initial conditions that are going to be automatically transferred in the cross-validation. Okay, so let me hop over to the demo now. Okay, so for the cross-validation compute type, first, just take a look and see that we have these calibrated simulation runs, right? So let's assume those are well calibrated already. And so if we want to create a cross-validation run, just like any other compute, you can come to the compute menu, go to your cross-validation manager, hit new, name it. And then you can just bring over whichever simulation runs you want to bring over. Maybe we'll just bring over all of those. Hit next, finish. Then we can come here on the compute tab and take a look at our cross-validation And so this is just showing you the different member runs that you select, or the different members that you selected. And those are just going to be the simulation runs. And then just for reference, you can see the basin model and the MET model. So you can't change those here because those are just connected to your simulation run. This is kind of similar to how the ensemble analysis shows your members, if you guys are familiar with that. And then you can also add members here too, if there's one not included. So that's just another way to add. All right, but let's go ahead and compute one. I don't know which one I'm supposed to be. All right. Okay, and you can see as it computes, it's going through, it ran kind of fast because it's a really small model, but you can see that it's going through each of the member runs as it's going. So because we had 3 simulation runs, there were 6 member computes or member runs altogether. So it went through each of those. Now we can hop over to the results tab. Okay, so just looking at the results tab, up top here for a given cross-validation, we have these calibration metric summary tables. And then down below, we have the actual runs, right? The actual results of this swapping that you did. So let's take a look at these first before we look at the calibration metrics. But so if you look, you see we have these. The first node in these tables, sorry, are the forcing, right? So you have a forcing April 1994. And what that's indicating is these are all the runs in which April 1994 is providing the forcing data, initial conditions and the MET model, control specs and things like that. That's just how we chose to organize it. And then if you remember with our naming convention, this April 1994, April 1996, that's April 1994 is the initial condition basin model, and then we are testing the April 1996 calibrated parameters on the 94 conditions, right? And then beyond that, it's set up exactly like a traditional simulation run. So all of this is the same as you would see for any given simulation run. You can click here, look at your calibration. That's actually pretty good for a cross-validation. And you can view that as you would any other simulation run. But let's hop back up here to the calibration summary table. So first up, we have the calibration summary tables for each of our 5 calibration metrics that we have in HMS. So for the Nash Soup Cleave, we can just look at this one first. These tables can get a little long, but what this is showing here is you can compare and see maybe which basin, which calibrated parameter set or which parameter set is performing the best overall. So just looking at this, you can kind of sort it this way. So we have the April 1996 calibration parameter set. We have the September 2018, and then we have the April 1994. So just like looking at those, April 1996 is they're all doing fairly well for a cross-validation, but April 1996 is consistently performing the best overall. So those are just the kind of determinations you can make based off of that. And then maybe we could look at a different one for the April 1996. So this is the, actually I wanted to bring up. I was trying to bring up the 96, 94 maybe. So this is the cross validation for the bias, the volume bias for the 96 to 94 event. And if we bring up like that calibration, or that actual hydrograph plot for that, you can see it's performing pretty well overall, as far as like matching the timing and the general shape, but we're lacking a lot of volume here, right? And so that's evident, and that we're at like negative 20% volume for that calibration run. So I think with that, that's all I had for the demo, and I will hand it back to Josh.
All right, thank you, Lauren. So Lauren just talked about the cross-validation compute, which is a whole brand new compute type in HMS. And kind of on a similar line, this next portion of the presentation is going to be about the frequency analysis. This has been around for a couple of versions now, but there have been a lot of improvements to it recently, one of which is a new stochastic compute option, which enables you to analyze uncertainty. So let me go ahead and pull HMS up. So a couple of things here on the frequency analysis component editor that are new to version 4.15. First off, you'll see that we now have a combo box for an observed frequency curve. So this is really geared for if you've done a Bulletin 17C analysis and you have frequency curves from that, you can now load those into HMS and it will be plotted as observed data behind your rainfall runoff computed flow frequency curve. So really cool to kind of combine the performance of SSP with HMS. So in SSP, I did a separate analysis and generated this curve. And then a second difference you'll notice here is there's now a compute mode. So the previous compute mode was deterministic, but now we've added a stochastic option. So I'll compute this deterministic frequency analysis, which computes pretty quickly. I have 9 ordinates set up, and each ordinate represents a frequency. So in this ordinate 1, I have the 2-year event, 5-year event, all the way out to the 1,000-year event. So I'm going to go over to results and look at the frequency curve plot. Let me make this a bit bigger here. So in the gray lines, this was the frequency curve from my Bulletin 17C analysis that I did in SSP. You can see that it has the computed curve, but then also has your upper and your lower confidence bounds. And in blue is what I get from the deterministic compute. So in this example, you can see that with roughly the 50 and 100-year events, they're aligning pretty well with the Bulletin 17C analysis. Definitely some work to do on the more frequent lower end of the curve here. So I could go into these ordinate basin models and maybe tweak some parameters. But the main point of this is that with the observed frequency curve addition, it can really help you with model calibration. All right, now I want to show off the new stochastic compute option. So let me go to this frequency analysis. So I've changed the compute mode here to stochastic. And you'll notice if you're familiar with the uncertainty analysis compute type in HMS, it's basically all of that functionality available to you here within the frequency analysis. So you specify the number of realizations or the number of samples that you want. You can specify your confidence level. And then what's different about this is that you can add parameters to randomize, similar to an uncertainty analysis. So in this example, I have a parameter that will basically sample different hypothetical storm temporal patterns. So if you've ever used the NOAA Atlas 14 temporal patterns before for your area of interest, you have 4 different quartiles. Each quartile has 9 different percentile flavors. So you have basically 36 different temporal patterns that you could apply to your analysis, and they have a big effect on the result. So as David mentioned before, you might want to do a sensitivity analysis on your temporal pattern, which is what this new capability is really after. And then secondly, I have a parameter that will sample different area reduction functions. So I have 5 different curves that I've computed from historical events, and I want to sample those as well and see how see the uncertainty bounds on my computed flow frequency curve. So I'll go ahead and kick this compute off. It's the same night ordinance that I use for the deterministic compute. Again, the only difference here is that I'm sampling for each ordinate 50 different combinations of temporal patterns and depth area reduction curves. So the ordinates, they compute one after another, but the 50 different sampling computes all happen in parallel. So that efficiency's carried over from the uncertainty analysis. Big thanks to Nick Van, who worked countless hours on parallelizing the uncertainty analysis compute. I've been able to leverage all of that hard work that he did by essentially using that same code here in the frequency analysis. So due to time here, I'm not going to let this go all the way through, but you can see, another minute or so, this would be computed. I'm going to cancel the compute and then just quickly look at some results of a compute that I did before the demo. Oh, that was the one I just showed y'all. Let me go to the right one. All right, so similar to before, but with this one, we now have rough bounds of your 95% and 5% confidence intervals. So we get that extra uncertainty aspect with this new stochastic option within the frequency analysis. Again, the only thing that I'm adjusting here are your temporal patterns and your depth area reduction factors, but you could throw any other parameters in there as well. Oftentimes your time of concentration will change from your frequent events to your rare events, so maybe that's something that you want to randomize as well. Loss rates also. So you can see even just with the different temporal patterns and reduction factors, it does result in quite a wide swath of uncertainty. All right, so let me get back over to the presentation here. That brings us to the close to the end here. Just wanted to have a big thank you to the USA's Flood and Coastal Systems R&D program that's funded all of the new features that we've showcased today. And a big thanks to Lauren and the whole Hypothetical Storms work unit team. There's been a lot of folks working on this guidance and these features, making it all come together. A favor to ask of you all, if you don't mind, we have a very quick survey. You can use your phone to scan the QR code, or David, do you mind dropping the link in the chat as well if people want to take the survey on their computers? There's 5 very quick questions that you can fill out, probably less than a minute or two. But really, we're going to actually use this information to try to determine topics of future webinars and what sort of documentation that we need to generate that would best help each of y'all. So we'll follow up with the results in a future webinar, but if you could just take a minute or two to fill out this survey, it would really, really help us and hopefully help us serve you all better. So I'll leave this up, leave this QR code up, but while we're filling out the survey, also wanted to circle back around to any questions. So if you have any questions that haven't been answered, if you want to drop those in the chat. A question for Tom, Lauren, David, are there any questions that we haven't answered here? Looks like we've answered most of them.
Not that I'm tracking. So if there's anybody out there on the call who feels like their question has not sufficiently been answered, feel free to go to the chat again and just remind us of that.
So I will just kind of highlight, I think all of these features that we showcased today are for version 4.15. So not available yet, but they will be available soon. And if you are interested in testing or providing feedback, if you can think of ways that these tools can be made to better serve your workflows, please let us know. Feel free to reach out to us, and we'll be happy to provide you a special build where you can test these features. So kind of bad news that they're not officially available yet, but good news is that you still have chances to provide input and hopefully make them better.
I was actually just typing an answer to Catherine, but I realized I can just answer it here. Catherine asked about if there's a way to change or keep which parameters are kept static for cross-validation. As it stands right now, it is all handled within the program. So we have certain ones marked as initial conditions that will be automatically kept static. And that, however, like for a future enhancement, we might allow more user flexibility in that.
All right, I'm seeing a question on the optimization trial. So it was the last webinar that covered a lot of the new enhancements that are coming out in 4.14 that will really help with automated calibration routines. So I'd recommend checking that out. I developed a lot of the features with the optimization trial. So if you have any qualms or suggestions for improvement, I'm definitely all ears on that. All right, we've got a couple minutes left if there are any other questions. All right. Well, I will go ahead and call this complete. I appreciate all of y'all for joining us today, and have a good rest of your Thursday. We'll see y'all on the next one.